Okay? So this is what Max just mentioned up here. This is what we have to remember for all functions. This is true for all functions. So if I want to determine the y-intercept of this function, I set x to 0. Take a look at what happens. 0, 0, 0. What happens to these three? They all? Cancel. Yeah, they all drop off. Cancel, right? So what are you left with simply? What do we call those numbers at the end of a polynomial? We're left with these numbers, right? This number here and this number here. What do we call those? Constants. We're left with whatever the constant was at the top over whatever the constant is in the bottom always. Is that clear? So that's our conclusion. It's very simple to recognize. We can look at simply the constants. We can look at the ratio of the constants to get the y-intercept. So for the first function, it's -3/6 or -0.5. Number 2 is simply an application kind of problem of this. Same thing. A stock value given in millions is represented by the following function as a function of time. Determine the initial value of the stock. Initial value simply means y-intercept. Think back, please. Initial value is the starting value or the y-intercept. So in this case, it would just be 7/4, okay, or 1.75. Because this was in millions, you'd say 1.75 million. So again, the y-intercept, simply set x equal to 0. Does everybody understand the notation that I'm using here? Focus, please. Everybody understand the notation I'm using with the 0 here, the 0 here? Okay, just evaluating the function when x equals 0 in both cases. All right, the second part, we're going to determine the x-intercepts. Now, before I show what's actually below, before I get into it, for x-intercepts, we remember that we have to set y equal to 0. That's the whole case here. We're setting y equal to 0. What's y? What's y in this function? I don't see y anywhere.
Is it n of x?
Yeah, it's whatever this is, right? Remember, your function notation is really the y-coordinate, always. So set this equal to 0. If that's the case, here's what I've got. Before I go down and show what the answers are, right? That's what I got right there. Okay? Now, ask yourself the following question, please, before you press on and make a common mistake. What makes a fraction 0? Only if the numerator is 0. Remember that, please. Okay, the denominator being 0, we already did that, didn't we? That's what gave us the vertical asymptotes. Remember, when the denominator was 0, we got vertical asymptotes. We care about the numerator being 0. What if the numerator and denominator have the same zeros, or the same factors? What do we call that?
Is it undefined?
It was undefined but indeterminate, but there was another type of shape we called it. It wasn't a vertical asymptote. What was it? When they had a repeated factor in the numerator and denominator, we called that something else. A hole in the graph? So it looks like, although the numerator might factor in certain things, if that factor cancels, it's not an x-intercept anymore. Okay, so let's get into this. So take a look at the numerator. Factor the numerator. Numerator factors into x minus 5x plus 2. Okay, x minus 5x plus 2. Are there any repeated factors in this one, between the top and bottom, is my question. Is there any factor that's in both the top and the bottom here? No. So we don't have to worry about any holes. So if I look at this, I take into account what Luke said. Luke said, you know what? When the numerator is 0, a fraction can be 0. So as a result, what do? You literally, right here, set the numerator equal to 0. This is the factored form of the numerator, set equal to 0. And then these are your solutions. So the x-intercept of this graph will be 5 and -2. So there's a lot going on now in your head. The denominator is what gave us vertical asymptotes. If it was repeated, it gave us a hole. Now, if it's only in the numerator as a factor, it's an x-intercept. So each part of the fraction is going to give us something else. We'll tie it all together in the next section of E4, where we're going to graph all of these. But for now, we're just going like one step at a time. This is, again, it's a relatively easy topic because you're kind of taking everything you've already learned and applying it to a new type of function, but it's not any different. Hey, you want the y-intercepts? We set x equal to 0 up here. Now we wanted the x-intercept. We set y equal to 0 down here. And then we solve through the problem. Yes?
How do you know the denominator?
Because what does the denominator being equal to 0 give us? A fraction that is undefined, right? So we already used the denominator in section E1. Remember we looked at the denominator's factors and we said, what makes the denominator 0? Well, that would give us the vertical asymptote. So we already took into account the denominator. So for today's practice, the question simply said, find the x-intercepts. So it didn't say find the vertical asymptote also. In E4, we're going to do all of this stuff. We're going to find the x-intercepts, the vertical asymptote, the horizontal, the slant, the y-intercept, all those things at once. But for now, we're just finding the x-intercepts. So my focus right now, George, is only on the numerator's factors. Okay? Second, or the next example with this, take a look at the wording, please. Take a look at the wording. The wording says the following. A particle's motion is represented by the velocity function. By the velocity function given in meters per second. Determine when the particle is at rest. When you're at rest, what do you know? I'm standing still. What can you say about the fact that I'm standing still? What characteristic can you define?
Motionless.
I'm motionless, good. If I'm motionless, give me a variable or give me some sort of a parameter that's not existing, or that doesn't really have a value.
Or I guess you're kind of like the constant, like you're not being multiplied by anything.
I'm not being multiplied. I'm not moving. I'm not changing. I'm a constant. Yes, but if I'm not moving physically, what about me is 0? My what? My velocity is 0 when I'm not moving, right? So for this problem, when it says find out when the particle is at rest, we're really just taking the velocity right here and setting it equal to 0. So when it says figure out when something is at rest and it's a velocity function, it's really saying set the velocity equal to 0. Whenever something is at rest, you're setting the velocity. The reason I asked the question this way is because in calculus, you're going to learn about position, velocity, acceleration. In physics, you're going to learn about it. This is a very common approach where you're looking at the zeros of a function and you say, well, the particle is no longer moving. Determine when that happens. Well, when it's not moving, what's the velocity? 0. So you set the velocity equal to 0 to do this. Okay? So we started the problem by setting it equal to 0, but then we look at the next line and we recognize right away, what do you notice that's different about this problem from the last one? What do you notice? What do you notice? What do you notice? Kate, go ahead. What cancels, Kate? It? What's it? Thank you. A factor in the numerator and denominator reduces. T minus 2 is in both spots. So T minus 2 will cause our denominator to be 0 when T equals what? When T equals what?
2.
Yeah, when T equals 2. So that's where the hole is going to be. Okay? Again, at T equals 2, we're going to get 0 over 0. Look at the fraction. Plug in a 2, you literally get 0 over 0. God bless you. When you get 0 over 0, we use the word indeterminate last class. And it means you have a hole in the graph. Holes. So as a result, we cancel the T minus 2, leaving us with 0 equals T minus 3. And God bless you, T equals 3 is our answer. Okay? The particle is at rest at 3 seconds. How about this one here? What are the zeros of the following rational function? What are the zeros here? Okay, all we have to look at here is thinking about the fact that the numerator is a trinomial, but it's x to the third. So what's the key for something like this to right away factor out? Yeah, take x out right away. Okay, once you take x out, it's pretty easy. It factors down to x plus 9, x minus 3. The x minus 3 cancels, leaving us with 2 factors. Now, recognize the x-intercepts are 0 and negative 9. What else does that tell me? And it's not even here. It's not written here, which is fine. What else does that tell me?
There's a hole at 3.
There's a hole at 3. Agreed. Agreed. A hole at 3.
Oh, you found the y-intercept.
Yeah, there you go. Nice. You have the x-intercept as 0, right? And the other x-intercept as negative 9. How do I write that as a coordinate? Isn't it negative 9 comma 0? And wouldn't this be 0 comma 0? So tell me, guys, what's the y-intercept for this problem? It's also 0. Look, if the coordinate of the x-intercept is the origin, it's also the y-intercept. Imagine putting a coordinate at the origin. It's both the x and y-intercept at only that spot. So whenever you get an x-intercept of 0, you can guarantee that the y-intercept will also be 0. Okay? Figure it out. Set x to 0. What do you get? 0, 0, 0 over negative 3. What's 0 over negative 3? 0. So the y-intercept is also 0 in this case. Okay, so for a problem like this, you could easily find both the x and the y-intercept right off the bat. And that's, I think, what you're doing for the last one, right? Yeah. So take a look at this last one. Try this one for a little while. This is going to be a little bit messy. This one's a little bit messier. How about you approach a problem like this? Be careful. Don't start on your own, please, because you're going to take a route that might be too long and you're going to be stuck there forever. What's the fastest way to solve a problem like this? Or at least try. George.
Set x equals 0.
We're going to have to do that to get the y-intercept, okay? We're going to have to do that to get the y-intercept. But I'm saying for the x-intercept for now, for the x-intercept. How do I find the zeros of this function, right? Don't I need to factor everything? Wasn't that what we've been doing? We've been factoring everything? So should I start with the numerator or the denominator? Why?
Because it looks easier to factor. I mean, you already know something easily to factor, and then it's
Okay, go ahead. What comes out easily?
well, x comes out, so you can have 2x squared plus 7x minus 4.
Yeah, so at least we've got some sort of a quadratic, right? So at least we can try and factor this. It's probably going to be a 2x and an x, and then like a 2 and a 2, or a 1 and a 4. So if you try with the bottom first, there's a good chance that one of those might repeat on the top to show a hole in the graph. So maybe using those factors on the bottom to take stabs at the one on top. Now the one on top is just going to be really messy. You're going to have to use synthetic table for the one on top, right? If you want to find the factors, you're really finding the roots. Okay, you're really finding the roots. So you could say P over Q is, plus or minus 1, 2, 3, 5, 6, 15, and 30.
10.
And try and 10, thank you. 10 and 30. And try those on a table. Okay? Now, what will end up happening? You'll end up getting the following factors. Again, this is stuff that you guys honestly can practice. There's no need to do this right now. But these are things you've done. These are the 4 factors this will become. Turned out that none of these, unfortunately, repeated. But it's all right, because look, now that you've learned section 8e, you should be able to factor this numerator. It might take a little while, but once you get 1 to work, you go to your subtable. Then maybe 3 works next, or 2 works next. You get another subtable, and then you can factor that last table to get the last 2 factors. So remember, if you're doing this, start your synthetic table, then go to a subtable as soon as you get the first root, then go to another subtable when you get the second root, and you can factor it pretty easily. And now that you know what the factors are, you can show the table if you want. Plug a 1 in on the outside and run it through. It'll work. Get another subtable. Plug a 2 in. It'll work, etc., etc. So there's nothing that repeats in the denominator and the numerator, so there's no holes in this graph. So it looks like we actually have 4 x-intercepts here. Okay, we have 4 x-intercepts here. To find the y-intercept, as always, we just set x equal to 0. When you do that, what happens? What do you notice? What happens, Kate?
Everything cancels, like all the x's cancel, and it's just negative 30.
Negative 30 over. But what's negative 30 over 0 as a value? Undefined. So what's the y-intercept? How could the y-intercept be undefined? How could a y-intercept be undefined, right? I get undefined if I do it. Plug in 0. I get 0. I get negative 30 over 0. George?
Well, I assume you're being a hole, but
It could be a hole, but there's not, right? Based on this graph. So what else could there be, George?
an irrational root.
Not irrational. You think an imaginary, but not imaginary either.
Does it maybe not cross the y-axis?
Maybe it doesn't
It's like
cross
a
the
parabola or
y-axis.
something that, like,
What's at the y-axis then? If it doesn't cross it, what do we call that?
An asymptote.
A vertical asymptote. So you were on the right track. Remember, when do you get a hole? When the factor in the bottom repeats itself, right? See this x equals 0 here? Aren't these the vertical asymptotes? Go back, guys. Go back. Take your brain back to E1. Is it there? Okay, good. Now, vertical asymptotes come from setting these equal to 0. So x equals negative 4 is a vertical asymptote. X equals 1/2 is a vertical asymptote. X equals 0. What is the line x equals 0, though? Isn't that just the y-axis? So the y-axis in this problem is a vertical asymptote. So as a result, you have no y-intercept. Okay? You have no y-intercept. When you go ahead and plug in 0, like we said, you get negative 30 over 0, which does not exist. There's a vertical asymptote there. Okay? Thoughts, questions? On a scale of really hard to really easy, where are you on this? Honestly. Really hard, really easy.
Is there like a middle part?
Sure, that's what I'm saying. So if it's really easy, you're here.
I'm dead.
If it's like kind of easy, if it's in the middle, if it's kind of hard, if it's really hard. Like, okay.
It's just kind of like asking about stuff.
Okay, that's the thing. I was just gonna say, in E4, in Tuesday's class, we're gonna put this all together, and I'm gonna go through the method of graphing these using all the things we've learned all at once. So for this weekend, all you need to think about is practicing E3, which is finding the X and Y intercepts for now. Okay, after this, we'll go into the other stuff. But over the weekend, you should also consider the fact that you need to get your project ready to be worked on Monday. If you're good about it, you should be able to finish on Monday, honestly. The project is not lengthy at all. This is an easier project. It just involves you guys doing your work on the side first to do that. So over the weekend, please do this. Please record anything you need to for your project, anything more you have to do. Have your data ready for Monday. If you want to, and you're really all about getting started ahead of time, because math is the first final exam this year, if you want to, feel free to even start over the weekend the final exam review packet. There is no problem set for this chapter, so you don't have to worry about that just yet. Okay? So consider that stuff. Look ahead, think ahead, what you can do. If you don't have questions, you can start the homework, at least get through it. You might even be able to finish. Right? What is it, 40-something today? 48? Yeah.
40.
So we're not used to these 8 days, right? When was the last time we had an 8 day?
No,
Honestly. It's like never anymore.
Everyone let out a sigh.
It's crazy.
It was weird, like
You're just not used to it, right?
I was
Like the
like, don't
beginning
find
of
your
the
work, and I
all
just
weekend.
showed, like,